All right, let's do the example I was going to do, and it's pretty similar to this one. So we have a triangular shape. The triangle is an equilateral. We have, just like in number 4 above, we have two joints with the ground. One is a pin joint, and then the other one is a pin and slot. But in this example, the slot is vertical, not horizontal. I'll call this member 1, 2, and then the joints I'll do A, B, C. There's a external load of 600 newtons applied at joint B. The members are each 3 meters long. And both of them at this instant are at rest, so there's no angular velocity. There are going to be angular accelerations, and we're going to have to calculate those. And what we want to calculate is the acceleration of that pin at C. So the basic, like the problem flow, we're going to start out by doing the rigid body problem, the rigid body kinetics for member 1 and member 2. Member 1 is going to give us one useful equation. Member 2 is going to give us 3 useful equations. Why the difference in the number of equations? There's a fixed point for 1, so we're only going to use the rotational equation. There's no fixed point for 2, so we're going to use both. Yep. No, those are up there. Oh, no, they're not. 10 kilograms each. Yes. I mean, unless there's 0. But the angular accelerations, like when we calculate them, could we make that a constraint, you mean? Okay. Yes, if that's going to stay an equilateral triangle, if it's going to stay an isosceles triangle, I guess this is the only place where it could be an equilateral triangle. Omega 1 and omega 2 have to be equal and opposite. But right now we're just saying that it's at rest, and then at that instant we apply this force to it. Okay, so we do the rigid body kinetics problem. We have 4 equations. Then we do the joint constraints. The first example we did last time, there was only one joint constraint. It was the knee. This one, there are 2 joints. One at B and one at C. So there's a little more work to do in this problem. And then the last step is the acceleration of the point C relative to the ground is going to be equal to the acceleration of the point C relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. The first term, the acceleration of C relative to the center of mass, is a circular motion problem, and the second one is one that we're going to have solved for with Newton's laws. Or it'll already be a variable. Okay, so first, body 1. Does that have a fixed point? Yep. So fixed. So A is A. And so that means that the mass moment of inertia, we're going to have to use the parallel axis theorem. So this is 1/12 times the mass times the length squared plus the mass times the distance from the center of mass to A. What's that distance? 1.5. And what do you get for this? 30? Wow. And then a free body diagram. The pin joint at A applies an unknown force vector. I'll call that the reaction at A. And then the pin joint at B, we have to decide which of these two members we're going to lump the pin in with. Okay. The way I always do it is I put it on the lowest numbered member, which means that the pin is part of member 1. So over here, we have the force vector on 1/2. We also have that 600 Newton force. That's, it's really applied to the pin, but our member 1 is that member and the pin. So 600. Our about point is here. And so the rho vector, force vector, moment vector. I will give $1 to whoever accurately guesses which step of this problem that thing is going to fall down on those guys. I predict it will happen during the joint constraint at C. Yeah. And the weight. Just kidding. Sort of. I mean, I don't know if I'm... keep I'll do a step and then look up and be like, and then go back to working. Okay, so the mass is 10 kilograms. So the weight is 98.1. So first I'll do the force RA. The rho vector from our about point to that force is 0. I'm going to just write these all as 3D vectors. So the force is RAX RAY, and it's a planar problem, so nothing in Z, and then the cross product is 0. And then the weight force, the row vector there is, so this is 60 degrees. What's 1.5 times 0.866? Can someone calculate that? What? Okay, it's 0.433 plus 0.866. Ooh, 1.299. Okay, so that's, which one is this? This angle is 30, so this is negative 1.299 and 0, negative 0.75, and then 0, right? The force vector is 0, negative 98.10. And what's the cross product? Zero, zero, 175 point, what, 127.5? 127.43 positive. And then the force F12, the row vector is twice this, so 2 point, negative 2.598 and negative 1.50. The force vector is F12x, F12y, 0. And what's the cross product there? Negative, oh yeah, negative 2.598 F12y plus 1.5 F12x, and 0 for x, 0 for y. And then the last one is the 600 Newton force. That also has the same row vector, negative 2.598, negative 1.50. Force vector is positive 600, 0, 0. And the cross product is 0, 0, 900. Yes. This has a fixed point, so no Newton's second law. Rotational equation says, so I'm just going to use the z components here. 127.43 minus 2.598 F12y plus 1.5 F12x plus 900 is equal to the mass moment of inertia, 30, times alpha 1. And I'll rearrange that into our first equation for our system. 1.5 F12x minus 2.598 F12Y minus 30 alpha 1 is equal to 1027 point, this is going to be negative 0.43. Who's with me on that? And then member 2. Does that one have a fixed point? Nope. It has those joints, but no point on it stays in place. So no fixed point, and that means that our about point is going to be the center of mass. And so the mass moment of inertia about the center of mass is 1/12 times the mass times the length squared, and there's no parallel axis theorem part. So that is 7.5. And then the free body diagram. There's a weight force of 98.1. Up at the joint B where the two bodies connect, there's a pin joint. And so we have the force on 2 by 1, which is negative F12. What about the 600 Newton force? That's not there because we associated the pin with member 1. So that only comes through to this member in the reaction force. And then at C, we have this slot. We have this pin and slot joint. There's the slot, and the force is perpendicular to that. You know, there's nothing restricting motion this way, so there's no force. It only restricts motion. You can draw that force whichever direction you want. I guess I'll put it in the positive x direction. That variable can come out positive or negative. I'll write that as the scalar RC. And then row vector, force vector, moment vector. Our about point is in the middle. So first I'll do this force negative F12, and I believe that row vector is negative 1.299, positive 0.750. The force vector is negative F12x, negative F12y, 0. No, that's right. And the cross product is 1.299 F12y plus 0.75. This is the component. 0, 0, okay. 1.299 F12y plus 0.75 F12x. And then the weight force is at the about point, so rho is 0. The weight is 0, negative 98.10. And there's no cross product. And then RC, the row vector is 1.299, negative 0.750. The force vector is RC00. And so the cross product Z component is 0.75 RC. Do we use Newton's second law for this one? Yep, because there's no fixed point. So we have, I'm only going to use the X and Y components. Z component is 0 equals 0. So negative F12X, negative F12Y, plus 0, negative 98.1, plus RC0 is equal to the mass of the body times the acceleration. I'll call that A2, and that is X and Y components. And then the moment equation says 1.299 F12Y plus 0.75 F12X plus 0.75 RC is equal to the mass moment of inertia times alpha 2. And this gives us our equations 2, 3, and 4. So equation 2 star says negative F12X plus RC minus 10A2X is equal to 0. Equation 3 star says negative F12Y minus 10 A2Y is equal to positive 98.1. And equation 4 star says 0.75 F12X plus 1.299 F12Y plus 0.75 RC minus 7.5 alpha 2 is equal to 0. Okay, so we have 4 equations. Before we count up the variables, anyone know how many we're going to have? 7, that's right. We had 6 when all we had was the knee joint. Now we have that extra joint that introduced one more variable, and that was that normal force RC. Okay. Variables now are F12, alpha 1, that's 3, A2, alpha 2, and RC. 2, 4, 5, 6, 7. That means we're going to need 3 constraint equations. But the increase in the number of variables that comes from each joint always matches the number of constraints on the motion that the joint provides. So even though we need more constraint equations than we did in the last example, we're going to have exactly the right number. So here's the deal. Here's how it works. This joint, because it's a tangent slot joint, restricted motion along the x-axis. And so we're going to have one more constraint equation that just says the acceleration of this point C has to be 0 in the x component. Okay? The x component of that has to be 0. But along with that extra constraint came the force that enforces that constraint, which is the normal force saying you can't go horizontally. Okay. So that's why you always have the same number of variables that you have equations after the constraints. Okay, so first I'm going to do the constraint at B. And that just says that the constraint, that the acceleration at B, according to member 1, has to be equal to the acceleration at V according to member 2. So we have to calculate the acceleration according to each of these two members, and then once we get these expressions, we'll set them equal. Any questions about where we're going? Okay, so first, member 1. The acceleration at B, according to member 1, this one has a fixed point, so we don't have to use relative motion. It's just circular motion around that fixed point. So we have 0, 0, alpha 1. Asked at the r vector from the center of the circular motion to the point in question. So that r vector, this point is moving around A. So that has to be negative 2.598. Negative 1.50. And then for circular motion, we add on this stuff. But we were given in this problem that it's at rest at this instant, so that goes away. So this is all we have to worry about. So we have, for the x component, 1.5 alpha 1. For the y component, negative 2.598 alpha 1, and 0z component. And now member 2. This one doesn't have a fixed point, so we're going to have to use relative motion. So the acceleration of B, according to the ground, is equal to the acceleration of B according to the center of mass of 2, plus the acceleration of the center of mass of 2 relative to the ground. Um, and so this says the acceleration of B is 0, 0, alpha 2 crossed with the r vector from the center of mass of 2 to the point we care about. So that's negative 1.299, positive 0.750, plus the centripetal part, which is going to go away. And then the relative motion part, the acceleration of the center of mass of 2 relative to the ground, is the variable that we're calling A2. And so for the x component, we have negative 0.75 alpha 2, let's see, plus A2x. For the y component, we have negative 1.299 alpha 2 plus A2y, and then zeros for z. And now we just set those two equal to each other. This one equals this one, like a long equal sign. Okay, so so to put these in the equations, I'm going to say the acceleration of b according to member 1 minus the acceleration of b according to member 2 is equal to 0. That's setting them equal. So our equation 5 star says, I keep forgetting this, 1.5 alpha 1 plus 0.75 alpha 2 minus A2x is equal to 0. And then equation 6 star says 2.598 alpha 1 negative plus 1.299 alpha 2 minus A2y is equal to 0. Any questions about that? Okay. So now we're done with the constraint at B. We need one more equation, and that's going to come from the constraint at C. Now I have to slow down a little and just to give that thing a little time to work itself loose. So for this one, we just have to calculate the acceleration of that point C according to member 2. The acceleration of C relative to the ground is equal to the acceleration of C relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. And so I'll rewrite this as the acceleration at C is equal to 0, 0, alpha 2, crossed with the r vector. This time our r vector is going from the center of mass of 2 to C. So that is positive 1.299, negative 0.750. And then, generally it would be plus omega 2 cross quantity, omega 2 cross r. But since this thing is at rest at this instant, that's 0. And then plus the acceleration of the center of mass according to the ground, which is our variable A2. So the acceleration of that point C is 0.75 alpha 2, 1.299 alpha 2, 0 for Z, and then I forgot to add on the acceleration. So for the X component, add on A2X. For the Y component, add on A2Y. Okay, and that's the acceleration of C. Okay, so how do we use this now for a constraint? What's the constraint we want? We want the X component to be equal to 0. So we don't care about that Y component of the acceleration. In fact, that's what we're going to try to calculate in the end. But we want to take the X component that we just calculated and set it equal to 0. So equation 7 star says 0.75 alpha 2 plus A2X is equal to 0. And that's just saying that the acceleration at the point C, X component is equal to 0. Okay, so to solve this, this is 7 equations for 7 variables now. We need an equation with 7 rows and 8 columns. A matrix, I mean, with okay, so that's 7 rows, 1 for each equation. There's 8 columns. And the variables are F12X, F12Y, alpha 1. And then I guess I'll do it RC, A2X, A2Y, and alpha 2. And then the constants. So now, can someone read me? So go back. We're just going to go through those equations one by one and tell me what variable is non-zero and read me the coefficient. So first equation 1. You're all like, we were only pretending to write this down. Okay. Okay. Negative. Oh, there's so many numbers. 1. Yeah, negative. Okay. Equation 2. Okay. Yep. Okay. And then negative 1 F12y, negative 10 A2y. Okay. 4. 1.299. Okay. 0.75 RC. Negative 7.5. Okay. 0. Okay. Okay. 1.299. Okay. Negative 1 and 0. Okay. Oh, and I can see the last one. Alpha 2.75, A2X 1 and 0. Ooh, let's solve it. We still have time. So F12. Mm-hmm. Okay, negative. And I'm going to allow, so we have a negative 2.6 in equation 1 and a negative 2.596 in equation 2, 598 in equation 2. I'm going to allow that because it would make the chemistry professors so mad. Exactly. What I mean, yeah. We almost finished this example last time. The problem looked like this. You have a hinge connected to a linkage like this. The bottom pin slides in a slot. And there's a 600 Newton force there. And at this instant, well, the lengths are both 3 meters. The masses are both 10 kilograms. At this instant, neither of these two things are moving. And if I label this one body 1 and this one body 2, and the joints A, B, and C like this, we wanted to calculate the acceleration of the pin at C. That might be being used to drive a gear or something, but there are plenty of engineering reasons why you would want to calculate the acceleration at a point like that. And we went through all of the calculations. We just didn't solve the final matrix. So what I got when I went through the matrix calculation is that F12 was negative 223.3, no, negative 2.3, 183.6. That's newtons. Alpha 1 was 7.23 radians per second squared. RC, so that's the normal force that the slot's applying to the pin at C, was negative 168.1 newtons. And that doesn't mean much if you don't know how I chose the direction of that normal force, but I chose the default direction of it this way, so that it says that it's a force of 168.1 newtons going that way, which makes sense if you think about what direction these forces would act. And then the acceleration of the center of mass of body 2 is 5.42 in the x direction, negative 28.17 in the y direction, meters per second squared. And then alpha 2, the angular acceleration of body 2, is negative 7.23 radians per second squared. The relationship between the two angular accelerations is something you'll see in a few of the problems. So look at this, the way that this linkage is set up. These two have the same length, right? So no matter what these angles are at, whether it's flat or pulled out, at any instant that has to be an isosceles triangle. Those two lengths are the same. And well, since this is horizontal, that means that those two angles have to be the same at every instant. Okay? And if they have to be the same at every instant, they have to be changing at the same rate. So the angular velocities have to be equal and opposite. The changes in those angles have to be the same, and then they have to be rotating opposite directions. And use that reasoning one more time, and the same thing has to be true of the angular accelerations. So we didn't use that as a constraint mathematically, but it comes out in the math if you do your constraints right. You could come up with a simplified way of doing this with a few, I guess you could reduce at least one variable by requiring that relationship. That would take some thinking, and I try to avoid thinking and just do the steps, and that's what I think you should do too. But if you're curious about it, see if you can figure out how to fit that in there. Excuse me. It is kind of nice to have that as a check at the end. Anytime you have one of these triangles where those angles have to be the same, just because of the geometry. Check your angular accelerations at the end and make sure that it's working that way. All right, let's draw the free body diagrams and stuff. Oh, well, let me answer the question first. So the question was, what's the acceleration of that point C? And so the acceleration of the point C relative to the ground is equal to the acceleration of the point C relative to the center of mass of body 2 plus the acceleration of the center of mass of body 2 relative to the ground. This is circular motion, so that acceleration comes from alpha cross r plus omega cross quantity omega cross r. And this one is our variable a2. So we just add that on at the end. One of our constraint equations was that this pin C at this location C, x acceleration. And so when we plug our values into this expression, we need to get an x value that's 0. If we don't, then something went wrong. But when you calculate this, what I got was 0 for x. I think it was like negative 0.0025 or something. You know, there's going to be some round up error, but basically 0 there, and then negative 37.56 for y. And so at this instant, if you apply this force here, this is going to accelerate down at 37.56 meters per second squared. Let's also, before I stop this, think about the total loads on this body now that we've calculated all this stuff. Well, we didn't. Okay, so on body 1, we didn't calculate this yet. We don't know what that is yet. We have a downward force of 98.1 there. And then the other end at B, we have 2 forces acting. We're assuming that the pin is part of member 1. That was the sort of bookkeeping decision we made. And so over here we have the force on 1 by 2. That's negative 222.3, positive 183.6. And then we also have a 600 Newton force that way. Yeah. And so I'll redraw this. We have the force RA over here. We have the weight force down. And then since the 600 Newton force and F12 act at the same point, that's just a single force vector. So we can think of that as a vector of positive, what's that, 371.7, 183.6. Is that right? Did I do that right? Oh, yeah. 377.7. I'm not going to do it, but how would you calculate RA if so? Why don't we know that, first of all? How did that not come up in our equations? Yeah, because when we isolated body one, we didn't use Newton's second law. That's never part of the steps that we follow. And so we just use the rotational equation, and our about point is at A, and so that doesn't produce any moment. And so that doesn't show up in the equations, even though it's acting on the body. And that'll always be the case for the body with the fixed point. But if you did want to calculate that now, you would use Newton's second law and go back. Now that you know what you're looking for, use Newton's second law and you can calculate that force. And now you could represent the acceleration of the center of mass in terms of the angular acceleration. So these would be the unknowns and you can calculate it. Okay, what about the other body? Okay, so up here, the only force at B on body 2 is negative F12, F on 2 by 1. So that's positive 222.3, negative 183.6. And then you have the downward weight force of 98.1. And then you have the reaction force at the wall with the opposite direction of what we said originally, with a magnitude of 168.1 newtons. And so now if you wanted to, for the people who are taking deform or who've done mechanics and materials type stuff before, if you wanted to figure out something about stresses and strains inside there, you can just, now that you've calculated those forces, you can just ignore the accelerations and stuff and just do the beam analysis on this member now. Assuming, like, now you can just assume that it's a statics problem. Yes? Right, that's right. Any questions about that example? All right. Well, the next topic is active particle kinematics. So we started out with particle kinematics, then we did particle kinetics, then we did rigid body kinetics. Now we're going back all the way to like the beginning, particle kinematics. But when we did it before, we did it in non-rotating coordinate systems. Now we're going to deal with rotating coordinate systems. So we already covered this, already did this in a non-rotating coordinate system. But there are a lot of times where it's helpful or necessary to use a rotating coordinate system, and it complicates things a lot. So I want to first just sort of explain mathematically a little bit and intuitively where the problems come from, where the difficulties come from with this. So first of all, the laws of classical physics only apply in inertial coordinate systems. So that means the coordinate systems can't first have accelerating origins or second have they can't change axis orientation over time. So that's rotation of the coordinate system. If you have either one of these, you can't do Newton's laws in that coordinate system. You can correct for these. If you have an accelerating origin, the way you correct for it is you use the relative motion equations. Okay, so you use the fact that the acceleration of the object relative to the ground, an inertial coordinate system, is equal to the acceleration of the object relative to your accelerating one, plus the acceleration of your origin relative to the ground. And so this one's pretty easy. Okay. We've been doing relative motion stuff like this whole class. This is the harder one. And this is what we're getting into now. Okay, so I'm going to try to illustrate by this I mean a rotating coordinate system. So why does a rotating coordinate system not work with the laws of physics? I'm going to do it mathematically, kind of. Just we'll identify where the problem is, and also just intuitively. So mathematically, the problem comes about when you take time derivatives in your coordinate system. time derivatives of any kind of vector in your coordinate system. So remember, in a non-rotating coordinate system, the simpler case, say you want to take the time derivative of a vector u, and this vector u can represent anything. It could be a velocity or a position or anything else that's a vector. So it could be a force or anything. We don't usually take time derivatives of forces, but this is true of any vector. So this is the time derivative of a vector with these components. And in a non-rotating coordinate system, how do you take that time derivative? So what's this equal to? This was like the first week or something. We went through some stuff like this. Yeah, it's just the derivatives of the individual components. And you can rewrite this as ux dot times I plus uy dot times j plus uz dot times k. It's just another way of writing it. Okay. But in a rotating coordinate system, if you take the time derivative of this vector, I'm going to think of it as ddt of, and I'm going to start by writing it out as ux times I plus uy times j plus uz times k. And if you take the time derivatives, you get ux dot times I, but then you have to use the product rule. And so each one of these gives you two terms. And if I separate this out, I can write this as so we can think of it as ux dot uy dot uz dot plus ux times I dot plus uy times j dot plus uz times k dot. And this set of terms is what, causes the difficulty. Because what are those things? I dot, J dot, and K dot, like how are we going to represent those in terms of values that were given in a problem? Okay. All right, so let me just try to help you kind of get your bearings on this. So notice whether you're in a rotating coordinate system or not, you're doing the same thing when you take a time derivative. Okay, you start out with this thing, you know, these components times the unit vectors in the direction of the axes. And derivatives always require the product rule. So you get this whether the coordinate system is rotating or not. It's just the issue that if the coordinate system is not rotating, then I, j, and k aren't changing in time. And so these extra terms go away. You know, these things are equal to 0 in a non-rotating coordinate system. Okay. When the coordinate system's rotating, these aren't 0. And so we're going to have to deal with it. That's the difficulty. Yep. Yeah, well, we're going to see that you can represent it in terms of the angular velocity of the coordinate system compared to the reference, the ground coordinate system. And that's going to be like the big result that'll let us do all the rest of the stuff. That's the result that everything will be derived from. But you know, when you first glance at it, you just have no idea how to deal with that. So, any other questions? Okay. So now intuitively, I want to just try to give you a sense of why you can't just use accelerations measured in a rotating coordinate system and plug them right into Newton's laws and just go on from there. So why don't kinematics calculated in a rotating coordinate system work in the laws of physics? Okay, so let's think about an example. I hope I didn't already give this whole example earlier. I get so excited when I think of it in the first week of class. Sometimes I draw it, but if you didn't understand what I was talking about the first time, here's a second chance. Okay, so here's an astronaut in training, future astronaut, hoping to be a future astronaut. And he's doing this thing where the seat whips around. He's like, why isn't anyone else's chair doing this? And let's think about two coordinate systems. They're both, at this instant that I have drawn here, they're both oriented like this, okay? But we're going to consider two coordinate systems. The first one is fixed at the axis. You know, it's not rotating. The second one is rotating with the arm. And that means that the passenger person is always along the negative x axis. So in the first coordinate system, just at the instant we're considering, the person just happens to be in the direction of the negative x. And the second one, that's moving with the arm, and so at any instant, the person's position is the length of that arm in the negative x direction. Okay. Okay, so what are the frames of like a film strip or whatever? Frame, are they called frames? Okay, so 3 consecutive film frames. So for coordinate system 1, I'm going to do first. Those are frames. Okay, in coordinate system 1, what do these film frames look like? So this is the one where it's not rotating. Here's the film strip. Okay, in the first frame, you just see the passenger coming into the frame, right? In the second frame, the person's right in the middle of the frame. And then in the third frame, the person's just leaving the frame, right? Based on those 3 measurements, you can calculate a non-zero acceleration. Okay, you can see that the person's moving. If there's no tangential acceleration in the motion, if this is a constant speed, then you still see that there's angular velocity. You know that there's a length, so you can calculate the centripetal acceleration. Okay. Force sensors in the chair. Measure non-zero forces. And F net is equal to the mass times that measured acceleration. Okay. In coordinate system 2, this is the rotating coordinate system. We'll do the same thing. Think about these 3 adjacent film frames. At the first instant, what does the camera see? Yeah, right. That's the key thing, is that camera is aimed at the passenger. Oh, that guy has some kind of bad genetic disorder. Okay, so um, position vector, the measured position vector is constant. So the measured acceleration vector is 0. Um, the force sensors still measure forces. Um, and so if you put these together, the net force that's measured does not appear to equal the mass times the acceleration. Okay, so if you want to use the acceleration you measure in coordinate system 2 and the rotating coordinate system in Newton's laws, you have to correct for that problem. Okay. Um, so to use Newton's laws uh, with measurements from coordinate system 2, you need to make corrections. That's the same thing if you have an accelerating origin of a coordinate system, you need to make corrections for your measurements, and we do that with relative motion equations. This is going to be a different approach for correcting it, but it's the same idea. We have to correct for what it's not seeing that a ground coordinate system would see. And also notice that, so I gave this kind of mathematical description and I gave this intuitive description. Notice that in both cases, the problem was related to what happens as time changes. It doesn't have to do with the single instant that we're talking about. It has to do with what happens in the immediate time vicinity of the point we're looking at. It's the time derivatives that cause the problems. Okay. Any other questions about this? This is like philosophy, so we can go deep on this one. Okay. Well, what we're going to see the big result. I don't know why it's in quotes, but that's what I'm going to call it. The big result. The big thing that everything in this section is based on is this. Um, um, if a vector is, let's say this vector, we'll call this vector u. So if a vector u is expressed in a coordinate system that's rotating with angular velocity omega, then the time derivative of the vector u is equal to the time derivatives of the components plus omega cross u. Yep. No, not necessarily. This we can do this in 3D. Um, the So we can go back into a full 3D spatial calculation of this stuff. It was only rigid body kinetics that we couldn't do outside of a single plane. So now we're back to sort of full freedom. And I'm going to write this two different ways. Each way is a useful way to think about it at different times. This is one equivalently. U dot is equal to U dot observed. Okay, so to an observer in that rotating coordinate system, that's what they think U dot is. Plus this correction. Okay, so like in that astronaut training example, this means the uh, true velocity of that person, of the passenger, that's the time derivative of the position, is the observed time derivative of the position, which is 0 because the observed position stays the same the whole time, plus this correction. Okay. Any questions about that? I'll give sort of give you a little bit of an understanding of where that comes from, and then we'll start applying that to other things. So to calculate, like, what's the true velocity of an object in a rotating coordinate system? Well, we'll get that from applying this to the position vector. What's the true acceleration vector? We'll get that from applying this to the velocity vector that we had just. Okay, that's all.